But for example, if rotation is too strong, turbulence is killed before being created.
Some rapid distortion.
Yes, it's true. And at high stratification, we have this kind of relation that the vertical displacement of particle particles is proportional to this ratio. So the would mean square velocity. So average, when distance mean average on the space-time box divided by the fluid basal frequency. This results has already been predicted by people like Canada, Pearson. Pearson has designed here. But Canada will diverge about the explanation, because in the simulation of Canada, the phenomenon in charge of the reduction of vertical diffusion is a phase mixing process. So it's linked to waves. In our case, thanks to the very low Prandtl number, our gravity waves are very efficiently damped from the beginning, and so we have just to learn. So who is okay? So the problem is that because my simulation were made in 2D with this kind of weird boundary condition along the Z direction, people said, okay, you have to confirm the result, especially because I explained that the vertical diffusion is reduced thanks to the strong anisotropic turbulence and not thanks to waves. In 2001, there was a strong battle between Nicolo and Canada about this problem, and I arrived in the middle just after. And so I said, just I want my paper published, and Canada said, okay. And finally, why not? And the results are published in Geophysical and Astrophysical Fluid Dynamics in 2006.
You have periodic boundaries, right? In the horizontal.
Yes, but not in the vertical direction.
Correct. But then, as things move back and forth, won't it have enough time finally to go vertically up? So, I agree that you are sweeping things maybe horizontally very fast.
Yes, but the problem is
there is no velocity, vertical velocity is very small, that's what you're saying.
Yes, yes. At high stratification, yes. That's what we observe. But the question is what would happen if we were 3D? Because Alain Vincent said, when I did my simulation in 3D, I saw no difference with the 2D case. Now, it's not sure. If we do, normally we must have normal diffusion in the Y direction if we do 3D simulation. If it is the case, the result must stay. If it's not the case, if the turbulence of the flow is a little bit different, the results will be a little bit different. But on global average, the question, you see difference in local, but when you do a global average, maybe there won't be so much difference. So we have to investigate this to be able to answer to people who are trying to say, we are not convinced of this. So.
And what is stratified?
Stratified is
what is being stratified?
It's a stratified in temperature. It's because we are at the top of the radiative spectrum, so we are stably stratified. And when we increase stratification and the initial horizontal velocity, so if you accelerate at the origin the velocity a little bit, you see this high stratification appearing. And so the way to see this in the anisotropic coefficient, because our purpose was also to have as much as possible a large range of anisotropy to see if, when Vincent said we can go up to 100, it's meaningful. It's not really meaningful, in fact. So here you have the passive scalar and the vorticity.
Is this self-sustained turbulence or is
yes.
it dying out?
Yes, self-sustained.
But I thought that...
Because you have the forcing.
Yeah, it's driven.
It's driven?
Yes, driven.
Okay. So the shear profile is kind of driven.
Yes,
And
but
that doesn't
you see,
fit.
after a certain time, it's not so. It's important, but it's not the major contribution because the amplitude of the velocity is much higher than the amplitude of the forcing. The amplitude of the forcing is equal to 1, but the velocity after. But at the beginning is very important because the velocity is equal to 0. So, but when the curvilinear starts, after you see it doesn't need a lot to be driven, and it was very interesting for this point of view. And here is the less stratified and the highest one, and this is a vorticity. So you see, if you don't have enough shearing layers fastly, the tracer can reach the boundary. And in fact, our space-time box is mainly controlled by the less stratified case. We define the time-space by the time for the less stratified case to reach the top and the bottom of the box. Okay, and so my expectation is to do this simulation in 3D with a pencil code with a periodic boundary condition to try first to see if these results are meaningful. Because all the analyses I've made, I have developed for the code to do the analysis. Just I need the file, the fields, and I'm able to do the analysis by myself. So, okay, and so also another point. When I came back from Montreal in 2005, I spoke with Bartolo. It's a professor of Department of Climatology and Oceanography at McGill, and they are doing the same kind of simulation but for higher point number because they are working on the stratosphere. And also they have a problem because in their case there are gravity waves and turbulence, and they are studying the gravity waves breaking to feed 3D turbulence. So they are interested by this simulation to see in 3D what it is, because they find the same kind of results, but they are not able to share between gravity waves and turbulence, and they are not able to really simulate the breaking of gravity waves. Is that feeding small scales or large scale, but the break of symmetry is normally more small scales because now we see the spectrum going up, so it's less steepy. So it's a way of investigation. So for the local study is finished. Now it will be faster. I'm working on the global star, so it's an axis symmetric star. And so you have the main hypothesis. And we are in the case that we assume overshooting. In fact, in the star, initially, we assume no pre-existing turbulence in isotopic and isotopic anything. And in the star, the star rotates with an initial conservative rotation law. This law is defined omega depending on the distance to the radius. What is the philosophy? Before studying the instability and the turbulence created and the vertical transport of chemical species, we have first to be able to know what is the evolution of the rotation law along during the evolution of the star in main sequence. In the standard model, so I don't go much in the standard model, but the standard model is one-dimensional, and the Kippenham equation are modified to take into account what I call the Scherer rotation, and omega depending on the radius. Our point is to try from the original equation 2D to go from a conservative law, because the original equations are valid for a conservative rotation law, to the Scherer one without doing the approximation made in the standard model. And when we have this law, you you will have the pattern of the velocity field to be after the study if in some part of the star, especially in the relative part. Here, my interest is for stars in the convective core. If we have some development of Kelvin and Morse instabilities and turbulence. Briefly, a conservative rotation law is a law which, under a theorem, a well-known theorem for people in evolution called the Poincare-Evac theorem, the total potential of the star can be written as a sum of the gravitational 1 plus an integral depending on the rotation law. When the rotation law is constant, you have this term. So what people are doing, actually, with a standard model with constant rotation, in the equation, they replace the gravity by an effective gravity taking into account this term. And when the rotation law is not constant but differential and conservative, you have an extra integral. And what I have made, I have computed this extra integral in the momentum equations. So this is a shape of a conservative rotation law. So omega 0 is a rotation in the case of beta equals 0. So it corresponds to the rigid rotation. And here, beta measures the departure from the rigid, the constant rotation case. And when you increase beta, your rotation law is more and more differential at the beginning. Okay. In the same time, when you compute, so this correction is momentum equation, so you are obliged to take the gradient. So you compute this in dr and dθ equation. If you want to generate a flow, because it's my purpose to study the instability developed in the flow generated by the rotation law, you can, from a consideration that a total potential can be a total potential defined in a kind of conservative law. It defines a surface. If you add a correction to the surface, you can take the vectorial product with, for example, the azimuthal component, but the unit azimuthal component, and you obtain two components which correspond to two components of the Coriolis force. And when we identify to a definition, so the regular definition of the Coriolis force, I mean an angular rate vectorial velocity field, you obtain the velocity component associated to the rotation rate. So in fact, it's the field, the flow generated by the rotation rate. So I don't explain this because we do a decomposition equation and we are obliged to do some approximation to reduce the correction of the equation to 9 terms, but it's consistent. So the code I am using is called the code Rotork. It's a code which comes from CIPA, Toronto. It's written, it was initially written by Bob Dupré, my boss at University of St. Marie. So it's an axisymmetric code. So it depends, it's spherical. It's in spherical coordinate, but it's axisymmetric. And we solve all the set of equations, so the traditional set for evolution, plus the conservation of the total mass and the definition of the external gravitational potential of the star. And we solve this with what we call the numerical, the MV method. So what is the MV method? You have a beam, so at a point, you have a point here, EG, so UK is written on this point, and the coefficient of, so you have 5 there, and the 5 coefficients are matrix depending on Jacobians. And you calculate in all the stars all the Jacobians, and after, so you go from the surface to the center, and after you solve this problem. So it's simply, it's the same way as solving a radiative transfer problem. After you integrate from the center to the surface to have all this value, and in fact exactly what you calculate is the perturbation of this value. After you have a Newton-Raphson method, and you iterate this calculation in all the stars up to the end. Your perturbation doesn't change a lot, and you define a new models like this. And that the new models taking into account all the variations.
You are solving for the stellar structure, the structure of the star.
Yes.
So you are also putting some reaction networks of all the.
It depends. If you calculate the ZAMS model, you can modify the differential rotation. So you have to reiterate to find the new models. If you do evolution, you start from the ZAMS model and you iterate and find. And so the problem is to have the right time step to be able to converge. Not to have instabilities, especially at the surface of the star or in the center. And the boundary conditions, so we have along the axis, so we calculate, we can calculate a meridian plane, a complete one, but we reduce, we take equatorial symmetry at the center, and at the surface of the star, the condition are precise. But we are obliged to define a scheme to the star. So, to give to you an example of ZAMS model, for example, it's a verification for people working on this topic to try to simulate the ZAMS model with the highest equatorial velocity, with the highest differential rotation inside. But we have some requirement to satisfy. If you read the theory of Maclaurin and Jacobi, Maclaurin ellipsoid, if you calculate the ratio between the kinetic energy and the gravitational one, you know that up to 1378, you have mainly a Maclaurin ellipsoid, which is an axisymmetric ellipsoid. So our code is able to calculate this because it's an axisymmetric one, but above this value you have two geometrical configurations, the Jacobi one, which is not necessarily an axisymmetric one, and Maclaurin one. But above this value, Maclaurin ellipsoids are harder and harder to obtain. So this is the reason why I present to you for this mass the highest ratio I could reach and the highest differential rotation I obtained. So here is constant rotation, and here is the highest I obtained, and we see a strong decrease at the pole. So there is a reduction factor of 2, and so the star is extremely flattened. At the same time, you have the surface temperature. We calculate the surface temperature. So we obtain what is normally known and accepted, an increase at the pole and a stronger decrease at the equator. This is for the ZAMS model. We are able to calculate. So
these are all highly distorted stars.
Yeah. Yes.
And because of rotation.
Yes, differential rotation. Yes. So
Does one see such stars?
So just so. People are very involved in this. The problem is now I can evolve the code with this kind of structure, and the problem is that if the star is too distorted, and so you can have any mass, any equatorial velocity, and any differential rotation. It's not meaningful from the evolutionary point of view. Here, so you have the two cases, So in fact, I have the results since 2 weeks. And you have here 6 of 5 pharmacy stars and 10 pharmacy stars. And here you have the profile of the conservative rotation law, and it's omega at each angular zone varying from the pole to the equator. And what we observe is, and the equatorial velocity is lower than the previous one, is 243 meters. And we have moderate differential rotation, beta equal to 0.4. And what we see during evolution is that the trend of the law is to become, to show Schiller pattern. Schiller pattern means in fact that on isobar, the angular rate must stay constant. And it is the case. But if you increase beta, for example, I try beta equal 1, I don't succeed in to stabilize the structure of the star. What I see, in this case, for intermediate mass stars, you need a certain time at the beginning of the evolution for the star to find, so there is interaction between the geometrical deformation of the star, the flow generated by the rotation law, and the rotation law. And the stars need to find an equilibrium with all this stuff. And for an intermediate mass stars, it's 2 million of years, so it's about 5% of the lifetime of the star. But for a more massive star, it's very fast. It's 10 times faster. So very fast you reach a quasi-Schiller pattern. But the difference is that if you go to lower mass stars, the core want to rotate faster during evolution than for higher mass star. And we see here a tendency that I was looking for is for higher mass stars, in one part is more flattened, in the sense that what I heard that observation of quite high mass stars show no differential rotation at the surface. So now my purpose is to push ahead in a sense that if you go in, if you follow the logic, if you decrease the mass of the star a little bit, and if you decrease equatorial velocity, you might be able to reach higher beta, and in this case, probably the internal rotation is higher, and here you have a slope enough important maybe to create some significant sharing here and to generate something which could bring some sharing turbulence and the no for the vertical transport. So, as I said, investigation of lower mass with lower angular velocity and stronger differential rotation. So I would like to reach beta above 1. And I would like to use the pencil code to investigate this nonlinear evolution, because I have the rotation law. You see, after the relaxation, this period of relaxation, when the star must find its equilibrium with the rotation law, after the rotation law is quite fixed. And I would like to study its nonlinear evolution and to see, for example, if it could become turbulent. In fact, this kind of simulation could be considered just as clues, because if the shearing is significant and could affect the transport at the same time, could affect the evolution, the time life of the star movement sequence. So just it would give clues that we are going in the right way. That's it. That's it.
Okay, so any questions?
About the in the first part of your talk, when you did your simulations with the different A's, can you remind me again, maybe I didn't listen, how you actually produce these different A's? Because that was no longer the composition of Kolmogorov and...
In fact, we increased at the beginning, we increased the value of n, so we increased the we increase the stratification, so the gradient of temperature, and we increase a little bit the amplitude of the initial horizontal excitation. So, in fact, the problem is it's mainly we increase the stratification. We increase a little bit the amplitude of Vx to gain time in the development of, but not too much. I mean.
So the forcing function is originally an isotropic one, and then you are somehow scaling the horizontal components by a factor, or how? What do you mean? In the forcing.
The forcing is this. The forcing is this. The amplitude is 1. But we start, for example, at the beginning we say, okay, we put just a forcing, we create a field.
The forcing for the shear, you mean?
Yes.
No.
At the beginning we have 0. We take this and we create a field. And after we restart the simulation and we multiply the horizontal component by a coefficient to accelerate the appearance of the terminal instability. But mainly, we increase the stratification, temperature stratification, that is the gradient.
Yeah. And the turbulence itself is really just the result of the shear. Wouldn't say that?
No, shear and stratification.
Yeah, that stratification modifies it, but
Because
even in the absence of stratification, just with the shear, would you already get turbulence?
Yes, we would have, but the problem is that our problem is time stratified. So, we are trying to do something corresponding to the top of the gradient, so it's time stratified.
But that's the question of
but it's right if you, it's more, yes, we needed this stratification.
Yes.
But it's right if you have just a shear. But in this case, you have the upscale. If you don't have stratification, you can have the upscale of the Commodore type. In this case, you don't have the upscale because thanks to stratification, you can go down to the small scale. So in 2D turbulence.
And this, so this is a regular reflection point instability, right?
Yes.
Inflection point instability.
Yes,
and
yes.
so there is a critical Rayleigh number, a Reynolds number, for this to occur, right?
In fact, we have mainly based our study about the Richardson period. In fact, to be able to use the Richardson threshold, you have to be sure that the second order derivative of the velocity is not known. And so we have checked that we have an RTH, because if you read the theory of Chandrasekhar, if you have an RTH and you have perfectly, I explained this in the annex of my thesis. We are exactly in this case, and when we solve it corresponds to some marginal case or something like this. And from this point of view, we are correct. Right. So I know that it's really questionable from the turbulence point of view, but the star is so big that you are obliged to simulate small parts. You see, for example, I would like to be able to simulate these shearing layers involved by the circular motion in all stars, but the Quadrille talk is not able to do this because I thought about what you say to me about the value of the celerity, and in my simulation, I am in the best case. I can't improve in a way that I could be lower than 10 minus 6. I am in the best case. If I try to, if I really, it's the way they do. So Bob does some idle simulation with this code. What he does, he does evolution. He stops. It drops the time scale. So the time scale is around 10 minus 5, 10 minus 4. It drops to 10 minus 15. And he calculates idle. So he said, okay, I take just a momentum equation, energy equation, and I see what is happening in the convective core. But, I wouldn't like to do this. Dropping my desk at the time scale is no sense for me because the secular motion is intermediate between the evolutionary motion and the hydro-time scale, what we call hydro-time scale. So I can, it's the same problem as the separation of scalar turbulence. I can separate my time scale. I need to have the full range. So I need to be able to simulate hydro in the same time as the motion. Up to now, no one has been able to do this. And most of the time it's a question that the code is not able. What people are doing in evolution with the standard model, they are using the code Geneva Toulouse model. So at Geneva, Mrs. Charbonnet calculates the diffusion coefficient. At Montreal, Suzanne Talon calculates the meridional circulation. And at Toulouse, Olivier Richard used the code of Georges Michaud with microscopic diffusion to do evolution with all the information. It's the way we do now. But when we asked, for example, to Suzanne, what is the time scale of evolution of your meridional circulation? It's sustained by the theory. The theory said when, for example, you have a massive stars, your meridional circulation reach like this in asymptotic states, so there is constant. It's not so bad because my simulation shows that we reach a Scherrer rotation very fastly. But for intermediate mass, it fails completely. They say, okay, we know that it's not true. We can assume a meridional circulation almost instantaneously asymptotic. There is a time scale needed. And it fails completely for solar time stars. It's the reason why maybe so many people are always working on solar states. Okay, I'm not